Hello everyone, my name is Geis and I'm a research assistant at the Communication Networks Institute of the TU Dortmund University. My presentation is about a novel deep learning-based path loss prediction model which implicitly extracts radio propagation characteristics from geographical information. My talk is structured as follows. Firstly, I'm going to motivate our work in the context of realistic channel models for massive machine communications. Due to that, I'm going to discuss the limitations of classic radio propagation modeling and following present you the proposed DRaGon model. Then we're taking a look at some results to evaluate and validate DRaGon's performance, and finally I'm going to conclude my talk and give an outlook about future research. Propagation scenarios can be distinguished by the geographical characteristics, the associated user density, and the resulting requirements of the network. And this slide shows an exemplified cellular network that covers regions with different geographical characteristics and different user densities. It is challenging to model radio propagation effects for mobile communication systems, and this is getting more complicated due to the rising number of connected devices. But it is inevitable to do that, as modeling mobile communication systems is essential for planning future networks to ensure reliable and low-latent communication. And therefore, realistic propagation models are required that are more accurate than empirical propagation models, more computationally efficient than deterministic models, and models that are sensitive to variation in network parameters. So what are the limitations of those classic radio propagation models? On the one hand, we have stochastic models that are computationally simple, they're fast in calculation and provide a satisfactory accuracy, but as they do not model the scenario and obstacles are only modeled statistically, they're not able to mimic the complex real-world characteristics, and as a result of that, they're in most cases too inaccurate. On the other hand, there exist ray tracing models that model the physical effects of each ray and therefore provide accurate predictions, but due to this modeling effort, they're computationally expensive and time-consuming, as well as they're geographical data exhaustive, so they're often too slow, and for this reason, faster and more accurate models are required, as for example, machine learning-based propagation models. Yeah, to this category, the proposed DRaGon model belongs. DRaGon stands for Deep Radio Channel Modeling from GeoInformation, and this slide shows the overall system architecture, and I will present that in more detail in the following. As for training a deep learning model, a lot of data is required. I will start with the measurements. And context, we used multiple LTE measurement datasets. The first one aggregates drive test measurements collected in the city of Dortmund in different scenarios. The second one contains UAV measurements from the city of Aarhus that were collected in different flight heights. Then we have more drive test measurements from the city of Copenhagen. And as a last dataset, we have drive test measurements collected in the city of Wuppertal. And in total, these are nearly 400,000 data samples. Further, the corresponding EMB information is required, and based on the EMBs and the measurements positions in one scenario, a rectangular bounding box of the scenario can be defined. Later, we want to use an environmental model of the scenario, so we need geographical data for that purpose. So firstly, we included elevation information based on the European Digital Elevation Model. And in addition, we used OpenStreetMap data to obtain a building model later. OpenStreetMap does not natively provide building height information, so we used another model that incorporates such building height information and integrated the information into the OpenStreetMap data. To visualize the need of these height mapping, here's an example of the Dortmund urban scenario. On the left side, you can see the Dortmund urban scenario when only the height values included in the OpenStreetMap file are used, and on the right side, how it looks like after incorporating another source. Further, a pre-processing of the EMB information was necessary. Because the EMB positions were determined based on measurements, they were not entirely accurate and needed to be corrected manually. And in this process, also height information was added, since the EMB information only included 2D positions of the base stations. And furthermore, not all required channel parameters were available for the measurement values, so they needed to be compensated. The LTE measurement data is available for all scenarios as RSRP values. The relation between the RSRP value and the received power can be seen in this formula. And the received power can be also described by a simple link budget formula, depending on the transmitted power, the gains and losses of receiver and transmitter, as well as the pathos. And as there are no information about those parameters, assumptions need to be made for them. So the transmit power is assumed to be 40 dBm. The gains and losses are summed up to an EIRP-like value, which is here called epsilon. And lastly, the pathos can be determined by a channel model. For example, in this case, we use the UMAB analyzed pathos model to fit the epsilon value to the measurements. And here's an example from the Dortmund suburban scenario measurements. So the measurement data is plotted over the distance between transmitter and receiver, and here you can see the UMAB analyzed model fitted to the measurements. Then the Limousin framework is used to build an environmental model of the scenario, so therefore we are using the OpenStreetMap data as well as the elevation profile. And based on the measurement positions and the EMB positions, position input of transmitter and receiver can be extracted, and then a direct path ray tracing can be performed in order to generate the dataset samples. So for each position input pair, a feature vector and 2 image samples are created. So the first image sample is based on the top view of the direct path between receiver and transmitter. You can see an example of that here. For generating the top view sample, a square bounding box is placed around the receiver's position, pointing toward the transmitter. So the resulting image sample looks like this, and showing an area of 200 times 200 meters in this case. The second image sample is based on the direct path side view. So here you have an example of that, and in the resulting image sample, the receiver is located in the left edge middle. Up and downwards, a range of 50 meters is shown of the vertical dimension, and in the horizontal dimension, a 200 meter range is used here. So the resulting image sample looks like this. So for all position input pairs, those top and side view samples are generated showing different ranges of the surrounding area of the receiver and transmitter. And in addition, a feature vector is constructed, which includes position features, including the 3D position of transmitter and receiving. It includes direct path features like the 3D distance, the number of building intersections, the distance where the direct path travels indoor, the number of intersections with the terrain, and the distance of the direct path traveling through the terrain. And in addition, also channel defining features are used, like the bandwidth, the frequency, the fitted epsilon value, the path loss, which is calculated based on the UMAB analyzed channel model, and the transmitter power. So these dataset samples were generated for all 400,000 measurements, and then this data can be used to train the deep learning model. Yeah, how does the structure of these deep neural networks look like? We have the input vector X that is fed into a feature neural network, and we have our stacked image samples that are fed into a convolutional neural network, which is working in parallel to the feature neural network. Then the outputs of both networks is summed up and fed into a final prediction neural network, which then outputs the y-hat value. How the individual networks are structured is defined by the model's hyperparameters. To find the optimal hyperparameter combination, a Bayesian optimization was performed, and all the examined combinations are summed up in these parallel coordinates plots. For this hyperparameter tuning, the whole dataset was shuffled, and then 10% of the data was used for this hyperparameter tuning. The final hyperparameter combination was then chosen by filtering the results for small validation losses, and the remaining hyperparameter sets were then analyzed manually in order to derive the optimal hyperparameters. The resulting network structure looks like this, and now it's time to evaluate the DRaGon model. So firstly, All dataset samples were shuffled and then split into 80% training data, 10% validation data, and 10% test data. The training and validation data was used to train the model, while the remaining test data was used for the following evaluations. At first, the DRaGon model is compared to classic pathos models, and for this purpose, the DRaGon model was solely trained on the Dortmund samples. I will start with the Fries-based models, which performed worst in this case. These include the Fries free space propagation, the two-ray ground model, the Nakagami 2 distribution, and the obstacle model, which performs best here as it is the only model that considers geographical characteristics. But all of these models achieved a RMSE value of nearly 30 dB or even worse. The empirical models under investigation were the Winner2C2 analyse and the UMAB analyse channel model, which perform very similar and achieved a significantly better RMSE value of 9.33 and 9.61 dB respectively. It is expected that the raytracer outperforms empirical and stochastic models as it explicitly models the environment and therefore the ray's physical effects, but in this case it achieved a similar performance as the empirical models with a slightly better RMSE value of 9.24 dB. And lastly, the DRaGon model outperforms all considered models with an RMSE value of 2.7 dB. In order to analyze DRaGon's generalizability over different scenarios, multiple data aggregation approaches are compared here. This includes a scenario-wise approach where an individual split evaluation is done for each scenario, then a global approach where the model is trained using 80% of the aggregated dataset, while the remaining 20% are used for the evaluation here, and lastly a cross-scenario approach. There, for each subset, the model is trained on the remaining aggregated data, while the subset under investigation is used as the test set for evaluation. And as it can be seen here, the scenario-wise and the global data aggregation methods achieved a very similar behavior with a mean of 0 for all evaluation scenarios. And more challenging was the cross-scenario evaluation, as it reveals the structural differences between the training datasets. It can be seen here that the Dortmund and Wuppertal datasets perform best in the cross-scenario approach, which can be explained by the fact that the German scenarios contain measurements from similar environment types. Thus, the test scenario is covered reasonably well in the training data. In comparison, the DRaGon model underestimates the RSRP value for the Aarhus dataset, which can be explained by the fact that the Aarhus dataset exclusively contains UAV measurements at receiver heights up to 100 meters, and with higher flight altitudes, the loss probability is increased, and this is not able to learn while only ground-based vehicular measurements were used for the training process. So far, the DRaGon model has only been evaluated for positions for which a corresponding measure value exists. However, the model can also be used for the exploitation of entirely new positions, and for this purpose, the DRaGon model was used to create a radio environmental map of the Dortmund urban scenario for one of the 3 German MNOs, and the results of this can be seen on this slide. There, a grid with 10 × 10 meter cells was used, where the receiver is located in each cell's middle. So for each receiver-transmitter pair, the data samples were created and then fed into the trained DRaGon model. So in order to conclude, I presented you a novel deep learning-based pathos prediction method called DRaGon, which is a combination of expert knowledge and machine learning. And as demonstrated, DRaGon outperforms classic channel models when trained on the same scenario and performs even better than classic channel models when evaluated on previously unseen but similar scenario. In future work, we want to further improve DRaGon. Therefore, we want to increase the versatility and the quality of our training data, as machine learning models can benefit from additional training data. Furthermore, we want to use more geographical information, like including vegetation information, and utilize DRaGon in the context of machine learning-enabled network planning. So thank you very much for your attention.